Hello, chemists. Jolly again. This is a continuation of our alkenes and our alkynes. So we are going to, where did it go? We are going to be talking about adding halogens today. Okay. We are going to do all of the reactions at the top of the reference sheet. So we're going to do those. We're going to jump back over to the reference sheet. And where are you? All right. So this time, let me change colors. This time we are going to talk about this one, and this one, and that one. So there's 4 for the alkenes, and then there's just a few for the alkynes. So we're going to talk about hydrohalogenation first, which means putting a hydrogen and a halogen on. Halogenation means put on 2 halogens. And where is it? Halohydrin means a hydrogen and a hydroxide. Okay, so this one is an H and an X, an H and an X. This is Markovnikov's. This one's anti-Markovnikov's. This is 2 X's, and this is 1 X and an OH. Okay, so those are the ones that we are going to look at. Over to our notes. Sorry, we're going to zoom. Woo. All right, so for the very first one, it is called hydrohalogenation because we're going to put a hydrogen and a halide on it, and we've done this mechanism like a million times. All right, let's see. Who do I want to use this time? Maybe I'll use HI. All right, we are going to use a binary acid, which means it has to have the hydrogen connected to one of the halogens. And we are going to do just the basic addition here. So we're going to break the pi bond. We're going to put a carbocation in its place. And what kind of a carbocation? The Markovnikov carbocation. Watch out for rearrangements. And we have also created a good nucleophile. And then remember, they're flat. So we are going to create the squiggle. And that is hydrohalogenation. Okay, hydrohalogenation. Now, the order of reactivity, HI is the most reactive. HBr comes second, HCl, and we rarely use HF. HCl is extremely slow unless it's very substituted. HBr, beware, can go through different pathways, and I'm going to show you one of those in just a moment. And you can always increase it. Okay, there's ways to increase things. In this case, you could use the addition of a silica gel or an alumina, but basically that is hydrohalogenation. Okay, hydrohalogenation. Now, what happens, okay, when you have unsymmetrical? So this would be considered a symmetrical, and this one that we keep doing over and over is considered unsymmetrical. And so the unsymmetrical just means that you have this possibility and that possibility, but that is not the most stable carbocation, so that is why we don't show both of them. We only show the Markovnikov product because it's the most stable carbocation. And guess what? There's that little statement about Markovnikov. Okay, so everything right there means carbocations will form the most stable one, which is the most substituted, and sometimes we call it the rich get richer because the one that already has hydrogens get more hydrogens, but the other one, it gets the other nucleophile. Oh, what is there an exception to? Well, of course, there's an exception to everything, but we have to work at it. So this is the second reaction. This is also hydrohalogenation, okay? But if you don't want it to go Markovnikov, you're going to have to do something special, hydrohalogenation. Okay, so these conditions, and again, we're going to do a radical mechanism, and I'm not going to show you the detailed mechanism, but you are going to see this. This is called a radical initiator. That is a peroxide. So the only one that's going to do it with is HBr. So HBr and a peroxide, okay, can't use HF, HCl, or HR. HI, you are going to only get the anti-Markovnikov, okay? It is regioselective. So remember, if it favors a specific region, it's regioselective. If it favors a specific stereoisomer, then it's stereo-specific. I'm going to go to the whiteboard and we're going to do a compare and contrast. I have a screen that keeps popping up here. Okay. So we're going to look at both of them. We're going to look at the Markovnikov addition, and we're also going to look at the anti-Markovnikov. All right, so we're going to start with an unsymmetrical. And I'm just going to put HX, but remember HI is better than HBr, so forth and so on. And we are going to end up first with a carbocation. And then we are going to end up with hydrohalogenation, okay? So that's hydrohalogenation Markovnikov addition. If you want the anti-Markovnikov, you better not go through a carbocation. We're going to use a radical. And the way you're going to recognize it as a radical is right here. Okay, that's a peroxide or a radical initiator. That is going to go through a different pathway. And so we're not going to draw a carbocation. We're going to put it in the anti spot. So this is the Markovnikov spot, and this is the anti-Markovnikov spot. So there are two different ways to do hydrohalogenation. All right, well, we just saw the alkenes. Let's look at the alkynes. And where are you, alkynes? Right there. All right, so there's the alkenes. Let's jump over to the alkynes. Okay, there's only two under the alkynes. So if you'll notice, it's again just HX. So that puts on H's and X's, called hydrohalogenation. This one just puts on X's, but we haven't done that one yet. Okay, so we're dealing with this one. Hydrohalogenation will give you a geminal dihalide, a geminal dihalide. Go back to our whiteboard. All right, this time we're going to start with an alkyne. And just like we've done like a million times in the past, the first thing you do is break the pi bond, and you have to make a carbocation, and that is the most stable carbocation. So here's the hydrogen that we put on, plus X minus. Oh, look, it's going to attack, and it's going to make... Okay, so that is your first product, okay? This is a alkene with a halogen, or it's called a vinyl halide, because there's a halide, and alkenes are sometimes called vinyl groups, so it's a vinyl halide. But unless you stop it somehow, which is very hard, it's going to continue again. Oh, look, it's the same one. And you're going to end up with a geminal dihalide, a geminal dihalide. All right. Can you stop it? Very difficult. You may use one equivalent of the reagent, which in this case is HX. Okay, that is very difficult to do. It looks great on the board, but really, is there a way to only use one equivalent of the HX? Or, okay, in this case, we could do a different pathway. Sorry, different pathway. Really, the answer is no. Okay, it's really hard to stop this reaction. Okay, you can pretend on the board and just put one equivalent, but it's very difficult to stop that reaction. All right, so there is hydrohalogenation of the alkenes and of the alkynes.